Hello, and thank you for joining our webinar. My name is Chris Kellen, and I'm the Director of Engineering for GeoStudio. In today's webinar, we will review how a sigma W strength reduction stability analysis can be used to analyze and design a pile wall for stabilizing a progressive slope failure. The agenda will include a discussion or background on the problem. We'll review the theory of strength reduction stability analysis. Then I'll walk through the project definition, get into the actual GeoStudio demonstration, and then provide some concluding remarks. Pile reinforcement is a common technique used to stabilize active landslides or prevent deformation during earthen construction. Unlike a tieback wall, pile reinforcement is considered passive because the structure first picks up load when the surrounding soil deforms. Numerical analysis of pile reinforcement systems is complicated by a number of factors, including the three-dimensional nature of the problem, which can involve soil deformation between piles that have a center-to-center spacing exceeding the pile diameter, the depth of embedment relative to the unstable soil layer also complicates things. And finally, the stiffness properties of the soil relative to the pile govern the response of the system. There are generally two widely used techniques for analyzing pile stabilization problems. First, limit equilibrium stability, and second, the strength reduction stability technique. The limit equilibrium method is based purely on static equilibrium of a free body diagram. All stresses, including gravitational loading and pore water pressures, are resolved into forces acting on the free body diagram. This is also true of reinforcement like piles. We must presuppose the amount of resisting force mobilized in the reinforcement. In the case of an anchor, we may simply use the pullout capacity of the anchor and assume that load acting on the system. Pile stabilization is a little bit more complicated. Engineers often increase the shear force in the pile, which is the reinforcement load shown by the black arrows on the diagram, until the desired factor of safety is attained. If the shear load required for design, or to achieve the design factor of safety, is less than the pile shear capacity, then the system is deemed acceptable. Another common approach is to approximate the active earth pressure on the pile, which assumes that a full rupture zone is mobilized in the soil, and then to apply this earth pressure converted into a force as an opposite shear force in the pile. As before, the reinforcement shear force can be incrementally increased until the desired factor of safety is achieved, and then this value can be compared to the shear capacity of the structure. The key advantage of the limit equilibrium method are as follows. First off, a limit equilibrium analysis is easier to set up because it is commonplace in geotechnical practice. The stress-strain material properties of the soil or rock are not required, and we do not need to characterize the pile, including its bending and axial capacities. The main disadvantage of this technique is that the soil-structure interaction is not modeled. Stated another way, the pile resistance mobilized by the deforming soil or rock mass is not modeled, and therefore no information on bending moments, shear forces, or deformation patterns can be gleaned from the analysis. The alternative approach is to conduct a strength reduction stability analysis via a finite element stress-strain analysis. In this manner, we not only solve the equations of equilibrium using the finite element method, but the entire system is subject to the constitutive behavior of both the soil and the structure. As we will see in the upcoming theory section, the SRS method is essentially a derivative of a stress correction analysis, which seeks to ensure that all stress states within the system are in legal stress space. The SRS technique is advantageous because it is essentially an ultimate limit state and serviceability analysis combined into one. In limit state design, the SLS is concerned with ensuring that deformations are tolerable under working load. The ultimate limit state, on the other hand, is concerned with margins of safety against collapse. The soil structure interaction is also considered in this type of analysis, and so we can determine the type of load that occurs within the pile wall. The disadvantages, or more aptly stated, the challenges of this type of analysis is that it's an increment in complexity compared to a limit equilibrium analysis. It requires more effort to parameterize the soil and the structure constitutive models, and interpretation is slightly more difficult. Now, as we'll see, the challenge is certainly not insurmountable. Before going on to the demonstration, we need to review some fundamental theory. Now, we're going to start with not SRS, but rather a stress correction analysis. We realize that the stresses from an in situ analysis, which is our first step in all stress strain analyses, can often disobey the failure criteria for the soil or rock. The reason that this occurs is that we assume isotropic linear elasticity for all material models in the domain. Consider the diagram on the right. This is the stress invariant plot of deviatoric stress versus mean effective stress for a Mohr Coulomb material model. The first strength envelope is defined by our out inputs for cohesion and friction angle. These are considered the design values for a stress correction analysis. The state of stress, defined by the stress tensor sigma naught, is sitting above our strength line. We can use these Cartesian stresses to calculate the corresponding stress invariants P' and Q'. The dashed line through the stress state represents a Mohr Coulomb strength envelope defined by pseudo-characteristic strengths. The question is this: what value of friction angle and cohesion could I use to create a failure envelope that passes through this stress state? To determine that, we use the Mohr Coulomb principal stress equation, shown here. With this equation, we sub in values for the friction angle and cohesion that are factored up by a partial factor, gamma m. So imagine then that we sub in, we solve for phi prime and c prime here, or phi and c, using these equations, and we sub it in to our principal stress equation for the Mohr Coulomb failure law, and we solve for a gamma m, a factor that factors up these strengths so that the line, the failure envelope, is passing through this point right there. What's important from the previous slide is that we know both the pseudo-characteristic strength parameters and the user input design design values, and we can therefore calculate a partial factor increment that reduces the characteristic strength to design strength. With this known, we can calculate a stress correction tensor associated with this partial factor. The stress tensor is integrated over the volume of the element, producing a forcing vector comprising x and y forces at each node, which is the boundary condition for the load step. The application of this boundary condition induces plastic strain and causes the stresses to be redistributed within the domain, bringing all stress states into legal stress space. Okay, so again, as I noted here, this is the theory behind a stress correction analysis. The strength reduction stability analysis is fundamentally the same as a stress correction analysis, except that in this case, the strength is reduced repeatedly by using increments in the partial factor until a global rupture is attained. The factor of safety must be interpreted using a variety of graphs, which I will review in the demonstration. Now, let's consider the case of a progressive failure on a weak layer. The geology comprises an over-consolidated silty clay overlain by a weak layer, a weak clay unit, and a sandy clay hill slope. The pile wall will be installed on the bench near the toe of the slope. We assume, for this demonstration, that this slope is exhibiting progressive failure due to continued shearing in the weak layer. In order to conduct a stress-strain analysis, we need to parameterize the material models for the soil or rock in the domain. At minimum, we require the effective elastic modulus and Poisson's ratio in addition to the unit weight. A stress correction analysis also requires strength properties, including the effective friction angle and effective cohesion. For brevity, I will not offer a discourse on laboratory testing. Instead, let's just review a basic oedometer test. The graph on the right shows an oedometer test result plotted first as void ratio, E, versus the log of axial effective stress. Then again we plot it as specific volume, which is 1 plus our void ratio, against the natural log of the mean effective stress. These graphs remind us that the stiffness properties are nonlinear. Taking the log or natural log removes some of the nonlinearity, allowing us to calculate the slope of either the normal compression line or the swelling line, which is sometimes called the unload-reload line. In log space, these parameters are called C sub C for the normal compression line and C sub S for the swelling or unload-reload line. In natural log space, these two parameters are often called lambda and kappa. The 1D constrained modulus can be calculated as a secant or tangent derivative of the curve in arithmetic space. This is usually done within the working stress range. For example, we would use the unload-reload line to determine the modulus if the maximum expected stress is less than the pre-consolidation pressure. Moreover, we would choose a point on the curve that represents average stress conditions in the field. Next, we need to go from the 1D modulus to the general elastic modulus for the soil. For a normally consolidated soil, we can use Jakey's rule to calculate the at-rest earth pressure coefficient, K0 NC, as 1 minus the sine of the effective friction angle. Conveniently, we can then back calculate Poisson's ratio using the relationship shown here. With Poisson's ratio and the 1D elastic modulus known, we can calculate the general isotropic linear elasticity, E prime, according to this relationship shown here. Knowing this then, and for this particular problem, we have the following material properties. The unit weight of all three layers is set to 20 kilonewtons per cubic meter. The effective elastic modulus for the lower unit is significantly stiffer than the upper two units. For demonstration, Poisson's ratio was set to 0.4 for all materials. The effective friction angle of the weak clay is 10 degrees, representing a residual condition. And finally, I will note that the volumetric water content and saturated conductivity of the materials will define. I'll talk more about why we use a VWC function in the demonstration. Okay, so here we are in GeoStudio. Now all numerical analyses have a basic workflow that includes creating the geometry, defining and applying the materials, defining and applying boundary conditions, solving, and interpreting. So step number one then is to create our geometry. Now in the interest of time, I've already done that by clicking on the Define Project button, going to the top of the tree, and adding a 2D geometry. GeoStudio is a multi-geometry, multi-physics package, and so we can include different geometries in the same project file, including 3D. Then, onto this geometry, I'm going to add a SeepW analysis by right-clicking and adding SeepW steady state analysis. The reason I'm doing this is to establish the correct pore water pressure conditions for our sigma W stress strain analyses. I'll close this dialog box and I will click on Define Materials. I have already added and named 3 different materials in the file. We add a new material and then we can change the name and select the appropriate constitutive model. In this case, our 3 layers are using a saturated, unsaturated material model. This material model requires both a volumetric water content function and a hydraulic conductivity function. For a steady state analysis, we don't actually need the volumetric water content function because there are no changes in storage with time. However, and as a matter of general workflow, we usually start with the VWC function because we need it to estimate the K function. Now for this analysis, what I've done is I've gone to the Define Volumetric Water Content Function dialog box. I've added 2 functions and renamed them. The first one gravel, the second one silty clay. Then with this named, I've gone to the Estimate button and used the sample functions built into GeoStudio with the water content or porosity input of 0.5 and then hit the OK button. I'll hit the Control key and select these 2 functions. Now, the reason I've created this gravel function will become clear when we look at the sigma W gravity activation analysis. But for now, what's important is that I've created a K function, only one of them, just for demonstration, using the estimation routine in which I selected the silty clay volumetric water content function, entered the saturated hydraulic conductivity and residual water content, which as a rule of thumb is about 10% of a soil or rock porosity, hit OK, and then now we have the function. Our 3 materials are completely defined. I will close this dialog box, select the Draw Materials, and apply each soil to the domain in the appropriate location. With that done, we can move on to boundary conditions. The left edge is going to be modeled assuming a far field total head condition. We know that water moves through this upper natural hill slope and discharges somewhere out here, and so we need a seepage face along this portion of the domain. And then finally, we either need a far field boundary condition, or in this case, and for demonstration, I will assume that the water table is at ground surface in the lower portion of the slope. I'll click on Draw Materials, then select the Define button. I've already added 3 boundary conditions to this list using the Add button, and I've renamed them appropriately. The drainage boundary condition is a water rate, or big Q, boundary condition with a value set to 0 and the potential seepage phase toggle on. The far field total head is a water total head boundary condition with a value of 14 meters. And finally, we have our 0 water pressure head. I'll close this dialog box and apply the 0 pressure to the ground surface. Apply the potential seepage phase to these portions of the ground surface, and then finally our total head, which is a value of 14 meters, gets applied to this left edge. Note that I've added a point to this line right here at elevation 14, so that when I apply the boundary condition, it doesn't get applied all the way up to elevation 20. With that done, I can now solve the analysis. As soon as you solve, it automatically switches into results view, where I'm now looking at contours of water total head and flux vectors by clicking on draw vectors. And we've added one to the list here. This is CW only analysis, so there is only one, and that is water flux, where we can toggle this on and off, set the magnification, or set the maximum vector length. Now this cluster of vectors that we see right here is simply due to meshing. All the vectors are roughly the same size. We see the seepage phase is not engaged in this area right here because the phreatic surface dips just below this corner, but water is discharging along this portion of the hill slope and then of course out the ground surface. Okay, now we have our pore pressures done, and so I will go back to the definition view, define project, and I'm going to add a sigma W in situ analysis. The first step in nearly every stress strain analysis is to establish the stresses and pore water pressures in the ground before we come along and apply a stress or a displacement boundary condition or model an excavation or an embankment construction and so forth. We have two options for in situ analysis, including gravity activation and the K0 procedure. For this demonstration, I'm going to use gravity activation. Notice that by adding this analysis into the tree, the parent analysis is automatically the steady state seepage analysis. I could change this if I wanted to by changing that to none. For demonstration purposes, I'm going to switch this back to steady state seepage and we'll carry forward. So the final pore pressures are defined to come from our parent CW analysis. Okay, again, for the workshop demo, I've already created the stress strain characteristics of the materials that I discussed in the presentation portion. We can see that by going to Draw Materials, clicking on Define, and just clicking through our three materials. The overconsolidated soil is using an isotropic linear elastic material model. The unit weight is set to 20. The response type is set to drained, which doesn't matter for an in situ analysis. And then finally, we have our stiffness properties. Young's modulus, 500,000. Poisson's ratio is 0.4. The sandy clay, the hill slope material, is using a more Coulomb material model. Response type is also drained. So the key difference is now we have strength inputs down here, where we've entered our cohesion and friction angle, and then finally the weak clay, which has a much softer modulus and a starting friction angle that's already likely softened down to 10 degrees. Okay, the materials that are used in the steady state analysis were automatically mapped onto our in situ analysis, so no further work is required to apply the materials. The next step then is boundary conditions. All stress strain analyses require constraints on the vertical edges and the bottom of the domain. As such, I will apply a fixed X boundary condition where the X displacement is set to 0 to the left and right edge of the domain, which is effectively a roller. And then along the bottom, I will fix both the X displacement and Y displacement. Now, while I do this, I'll note that a gravity activation analysis uses the unit weight of the soil to form a boundary condition. Okay, so it is the forcing boundary in this analysis, as we'll see here in just a second. And that is why I do not need to apply any other boundary conditions. With that done, I'll solve our gravity activation analysis. And we'll switch the contours over to Y effective stress. Let's ensure that we're off to a good start by using the draw graph functionality to double check our stress conditions. Along the left edge of the domain, I've added a new graph, set the locations, and chosen all the geometry items comprising this left edge. Then I changed the first category to total stress, second category to Y total stress versus elevation. And then to ensure that we're looking at Y or elevation on the Y axis, I right-clicked, went to options, and rotated the graph 90 degrees. Then I cloned the graph and changed the category to plot pore water pressure. And then I cloned the graph again and plotted Y effective stress. So just to make sure that everything is looking good, I will select the Y total stress, hold down the control key, and then select pore water pressure. And then finally, Y effective stress. Okay, so key thing, on this left edge, the water level is at an elevation of 14 meters. And then the water pressure increases with depth to around 160 kPa, and then it decreases negatively into the unsaturated zone. The total stress goes from 0 at the ground surface down to 473 at the base of the domain. And then notice our effective stress. The effective stress is the total stress minus the pore water pressure. And so that's why we see this green line right here. But what's interesting is that the total stress and the effective stress are equal in the unsaturated zone. Now the sigma W gravity activation or in situ procedure gives consideration to the water content in the soil. If a water content function is not defined for a material, then the negative pore water pressure is fully realized in the effective stress calculation. To demonstrate, I'm going to close this dialog box, go back to define, click on the materials, define, and then on the hydraulic tab, I'm going to set the water content function to none for all of these materials. With that done, I'm going to resolve our in situ analysis. We have the same pore pressure distribution, but notice that the Y effective stress contours have changed. If I click on Draw Graph, and once again multi-select these graphs, we now see that the Y effective stress up at the ground surface is no longer 0. It's 61 kPa, which is the opposite, the positive sign, of the negative pore water pressure. So again, by not including a volumetric water content function, we've artificially increased the effective stress in the unsaturated zone to equal the negative pore water pressure. Now it's for that reason why I defined a gravel function for this upper material, because I did not want to include the effect of suction on the effective stresses. Going back to definition and define materials, I will reselect these three materials, go back to the hydraulic tab, and change the volumetric water content function and resolve. Okay, with that done, we'll now go and do a stress correction analysis. Back in Define Project, I will add a sigma W stress redistribution analysis. I'll rename it stress correction. Notice that we have two different methods, stress correction and strength reduction stability. As I noted in the presentation portion, the stress correction analysis ensures that all the stresses in the domain obey the failure criteria for the soil. So this is an important first step before we go and do our strength reduction stability analysis. By default, since our in situ analysis or our gravity activation analysis is modeling pseudo-geological history, the default is reset displacements and strains for this new child analysis. As I noted in the presentation, a stress correction analysis forms a boundary condition by integrating the stress correction vector over the volume of the element. And so accordingly, we do not need to apply a boundary condition just like an in situ analysis. So I'll solve this and then we'll switch over to results view. Okay, in results view, again, we're looking at y-effective stress. Notice immediately that they are different. The stress contours are different from our in situ analysis. Again, this occurs because stress has been redistributed in the domain to ensure that all Gauss regions obey the Moore Coulomb failure criteria for this material. We can see that by turning on the View Plastic States, which turns off the contour coloring. Now, interestingly, the entire weak layer has already yielded, which I guess isn't surprising given that the material has a friction angle of only 10 degrees. We also notice that a rupture zone has yet to form in this soil slope, but clearly for a hill slope that's exhibiting continued movement, this is what we would expect to see. Now, before going on, let's check the factor of safety, the stability of the slope, without doing an SRS or stability analysis. Instead, I'm going to go back to Define Project and add a slope W sigma stress stability analysis. Now, this analysis looks into the stress field that we get from sigma, and it draws a slip surface and then calculates the factor of safety by integrating the shear mobilized and the shear strength over the slip surface. I won't get into the details. You can refer to the slope W and sigma W reference book for the theoretical background, but one of the advantages of this technique over limit equilibrium analysis is that it's quick like limit equilibrium, while at the same time it does not suffer from some of the convergence problems that we often run into in slope W. We have a slip surface tab. We're doing a left to right analysis using entry and exit. And so with that done, I'll close this and I will draw the slip surface entry and exit zones. Like so. And then start the solver. Okay, we see that the factor of safety is currently sitting at 1.235 with the existing stress state in the soil. Now I'm going to go back to the definition view and we'll add to this file a new analysis, sigma W, stress redistribution. I'll go to the Define Project. This time we want to switch to strength reduction stability. Note that in the strength reduction stability, our first inputs are the initial factor by which we're going to reduce the strengths of the soil. It's set to 1. We increment the factor in 0.025 increments up to a final factor of 1.5. The initial stresses and pore water pressures come from the parent analysis, which by default has been set to our stress correction analysis. I'll close this dialog box and navigate to the Draw Structural Beams. We need to include our pile wall in this analysis. Note that we already have a pile in the list. If I click on Define, we see that to define a structural beam, we need a modulus and a cross-sectional area, because E times A represents the axial stiffness of the structure. We also need our moment of inertia, because E times I is the bending stiffness of the structure. And then finally, for a two-dimensional plane strain analysis, we need to enter the spacing, because both the axial stiffness and the bending stiffness are normalized by the spacing to account for, say, an out-of-plane pile spacing where it's not contiguous, where there's actual spacing in between piles. I'll close this, zoom in, and I'll apply the beam properties to that line. This line is already meshed, and so we don't need to do any additional work. With that done, we'll solve the analysis. As the solver is running, we see the different strength reduction factors in the second column here in the results time window. And so we can click through the individual times, watching the plastic states. We see that as solve progresses, the plastic states begin to open up, indicating that all the soil in this zone is now at a state of failure, until finally we reach our last partial factor, our strength reduction factor, and we see this full rupture zone extending to the ground surface. Now I did get a little bit ahead of myself, and so I'm going to go back to definition view and clone this analysis, because I also wanted to ensure that we could compare to the case where the pile wall was not included in the analysis. So I'm going to click back here and remove the pile, and then begin running this analysis. Well, this one is running. I'll click back on the analysis with the pile, and we'll investigate some results. One of the key things to realize is that unlike limit equilibrium or finite element stability analysis, we cannot interpret the factor of safety just directly. It's more of an indirect approach. Okay, so again, this is with the pile included. I have a graph of lateral deflection near the toe, and we have a unique graphing category here. This is a mesh graph, so we're getting data from nodes in this case, and we're plotting displacements, specifically x displacement versus strength reduction factor. Now what's interesting in this plot is that we see the strength reduction factor at about a strength reduction factor of 1.325 to 1.35. We see the amount of deflections increasing. Now looking at the plastic states, so between 1.3, 1.325, and then 1.35 is when the toe displacements begin to increase markedly. And that, of course, as we can see, corresponds to this ever increasing size of a rupture zone extending to near the ground surface. By the time we hit 1.375, then we have a continuity in the failure surface. Okay, so that's one graph, is looking at some displacements of a key part of the domain. Another one is what's called domain stiffness. versus safety factor. What's important here is that we see the domain stiffness is around 0.35, and then at a strength reduction factor of 1.3, we see this abrupt decline down to 0.05. And so the domain stiffness drops precipitously at a safety factor or a strength reduction factor of around 1.325 to 1.35, which is similar to the value that we deduced from the X displacement graph. Okay, and then finally we have one other graph here, and this is the vector norm of displacements. Vector norm of displacements versus safety factor. Now, just like our other two graphs, we see that the vector norm changed quite dramatically at around a safety factor of 1.325 to 1.35. And so all of these graphs combined, our vector norm of displacements, our normalized domain stiffness graph, and lateral deformations of the toe, would suggest that with the pile in place, the factor of safety is around 1.35. Now let's click on our analysis that excluded the pile and see what we can glean. First off, stepping through the plastic states, we see the rupture zone has not developed at a partial factor, a strength reduction factor of 1.2. By 1.25, it's beginning to form. 1.275 and 1.3, we have a full rupture zone developed. Keep in mind that our finite element stability factor of safety without the pile in place after doing stress correction was 1.235 or around 1.24. So in this case, let's again revisit the graphs and see if we can deduce the factor of safety. Lateral deformation graph suggests that the factor of safety is just under 1.3, likely around the 1.275 mark, where we begin to see this change in slope. The domain stiffness graph, we see that at 1.25, we get this precipitous decline in domain stiffness. And then finally, vector norm of displacements is similar to our lateral deformation graph in that it's closer to 1.3, somewhere between 1.275 and 1.3. Now, all taken together, we could conclude that the factor safety is somewhere around 1.25 to 1.275, which is in keeping with our finite element stability analysis. Now, more importantly, we were reminded that in progressive failures, the slope is exhibiting continued deformation. Our main concern is not so much in the factor of safety, but in the ability for the wall to limit deformation. Let's return then to draw a graph and more closely inspect the deformations. Without the wall, we see that as the factor of safety is reduced beyond 1.3 and up to 1.5, the total amount of lateral deflection reaches around 0.3 meters or 30 centimeters. With the wall in place, we see that that deflection is limited to only 0.03 meters, so one order of magnitude less lateral deflection near the toe with the wall in place. Similarly, we can look at a graph of wall deflection, and we see that, yes, there is a very sharp demarcation in the deflections that we could measure with an inclinometer in the field at elevation 5.5 meters, but the overall X displacement in the natural hill slope above the weak layer is only around 0.03 meters with the wall in place. Without the wall in place, again, we see that substantive amount of displacement occurring in the upper portion of the profile. So let's have a look at the moments and shear forces in the pile. This is a graph for a structural beam. I need to be clicked on this graph right here. This analysis. We're plotting structural beam, and we need bending moment about the out of plane axes. We see that the maximum bending moment is around 120 kilonewton meters, and that is at a safety factor of 1.5. At our reduction factor of around 1.3, we would anticipate a bending moment of around 60 kilonewton meters. We could now take this information, compare our anticipated bending moments to the bending capacity of the wall to ensure that the wall is adequate. Similarly, we can clone this graph and plot the shear force distribution in the pile wall. Which suggests that the maximum shear is around 88 kilonewtons, likely in the range of around 50 kilonewton force. And once again, we could compare this to the shear capacity of the wall. Returning to PowerPoint, we can now conclude the following. First off, a volumetric water content function is useful when conducting an in-situ analysis to ensure that the effective stresses in the unsaturated zone reflect natural conditions. Without a volumetric water content function, sigma W fully weights the effect of negative pore water pressure on the effective stress calculation. Second of all, we use a stress correction analysis to ensure that the stress state of all Gauss regions obey the failure criteria for the soil. This is a critical first step in stress strain analyses. The factor of safety was 1.25, calculated using the finite element stress stability technique. We achieved a similar factor of safety using the strength reduction stability technique. With the wall in place and using SRS, we calculated a factor of safety of 1.35. We also saw that introducing the wall into the system, which carries the load as deformation occurs, restricted the amount of deformation, which was witnessed not only in the graphs of normalized domain stiffness and vector normative displacements, but also the lateral displacements at the pile wall location and the toe of the slope. We can also conclude that the key advantages of the strength reduction stability technique are that the failure envelope, or the shape of the slip surface, evolves naturally from the analysis. In contrast, we must presuppose the shape of the failure surface when we conduct a limit equilibrium analysis. Finally, the soil structure interaction of the system is simultaneously analyzed using the SRS technique. As such, the bending moments and shear forces that are mobilized in the pile wall are automatically analyzed with this type of analysis. Thanks for watching, and I hope you enjoy using sigma W in GeoStudio 2021.